Okay, can you all see my screen?
Not yet.
Not yet? Okay, hopefully it comes in pretty quickly.
I've got it.
Okay, excellent. Excellent. So here's the agenda for today. Um, Essentially, I want to cover any questions that you have, and then just a couple of the usual sort of logistics announcements. Um, and um, uh, and then I want to take a little bit of time to recap, just a tiny amount of time to recap hypothesis testing and confidence intervals. And I want to give you a paradigm that may help when you're putting together that framework. Um, and then today is all about regression and modeling. Now, a regression model is a type of model, but I want to start out with just a few sort of maybe I'll call them insights and observations on modeling, um, and then we'll get into regression. Okay, and regression, we'll give it its own sort of whoops, hello. Got fresh batteries in this thing now. Hopefully we'll have no technical difficulties today. Knock on wood. We'll talk. We're going to start from the start, which is the easiest one. We'll talk about simple regression, and we'll spend a decent amount of time on the framework there. And this is really just these are things that you probably already know, but we'll cover it for reals, as my kids say. This is basically when I have a scatter plot, when I have a relationship between 2 points, x and y, let's say height and weight of an individual, or it could be performance and experience level of a person. What we're going to cover is what if I want to fit a line to make predictions? What would be the equation of that line? Y equals b0 plus b1x. That describes this line the best. What's my best fit? Of all the fits I could make, what's the best fit? That's what simple regression is all about, and we're going to cover that in detail. We're not just going to cover the technique of how to do the line, but we're going to cover how do you do a regression safely so that you can actually use this for prediction. Because anybody and his brother now can fit a line using Excel. It'll do it for you. So there's not a heck of a lot of skill in just fitting the line. It's really understanding when you should do that and when you probably shouldn't, and what are the bounds on what you've done. And then the rest of this stuff in regression is what I'll call extensions. I don't need to write regression there. Extensions. And we're going to extend it in a number of different ways. We won't cover all of these today. We're going to cover one of them today, and then we'll take half the lecture to cover the others next time. Keep in mind that they are deeply covered in some recordings that you'll be able to see and in the notes in your book. So we'll cover the most important one today, and that is multiple regression. That is, what happens when more than one thing is related to Y, to our output, right? So you can think of performance of a person as being related to a heck of a lot more than experience level. How do we add those other things into the model? That's multiple regression. That's a super important one because it helps us make our models much more useful. So that's a great extension. Another extension that we're going to talk about is polynomial regression. Ugh, see if I can spell that. Polynomial regression. We'll leave that for next time. But that's a funky technique for what happens when we have a curved relationship. Well, we can probably use a polynomial to describe what that is. We'll talk very, very briefly about something that confuses a lot of folks, transformations. And the reason we're going to talk about it briefly is not because it's confusing, but because in some sense it's not worth the battle of unlocking that confusion. It is for somebody like me, for sure, but what I'd rather do is I'd rather take you through a simple example of what's there, show you how it worked and why I used it, and then also show you what's one of the downsides of using it. There's really only one downside, but that downside's a pretty big one. And it's in interpretation. Once you use it, it's like nobody, I won't say nobody, but people won't understand why you used it. And then finally, dummy regression. Hate the name, so sometimes people call it indicator. This is indicator variables. And this is very helpful when, what if I have everything that we covered up to here is I have a y that's a number and an x that's a number. What if I have an x that's a category variable? How do I deal with that? How do I add that in? Dummy regression comes to the rescue. And it's a very, very straightforward technique. But again, let's walk before we run. So we're going to cover simple regression first. We're going to do that first. Okay, hopefully that sounds pretty good. Pretty full plate today. Let me open it up to the floor and ask, are there any questions that anybody has regarding the assignment that's due, or any of the previous material that we've covered, the recent material that we've covered?
Mike, this is Steve.
Hey, Steve.
At the end of the last lecture, I'd had a question for you about how to set up this hypothesis testing, and you asked me to remind you to go over the whole setup in terms of the data collection and the next step that follows.
Right. Okay. Right. So thank you, Steve. So yeah, Steve and I had a bit of a conversation after the last lecture, and want to make sure that we get this. Hypothesis testing can only be done after you have data to test a hypothesis. Now, it may be obvious, but it's not always. There's so many things that we're doing here, so that it's not that obvious always. So if you recall, if you're going through your DMAIC process, hypothesis testing tends to come right here and also right here. Why right here and right here? Well, this is after you've already collected some data. Here's your data collection right here, or maybe here. You're collecting data, right? That's data collection. Oops, collection. All right. And so here you're basically testing, I have this idea. I wonder if, like, let's say I have a driver that says, let's go with our performance and capacity, or performance of a person, and maybe experience level. But here I'm talking about new employee versus seasoned employee versus very experienced. Maybe there's 3 levels of experience on this: low, medium, and high experience. Right? Or let's just say low and high experience. Okay, so that's a cat, and that's a num. I don't know how you're measuring performance, but presumably we could find some numerical measure of performance. I might have this theory that says, I wonder if experience level is driving performance. And when I do that, I draw that PGA wheel. Remember, I don't have to actually draw it, but I can use it in my brain to say, here's my English level question. This is the I wonder question. I wonder. This is my plot. If I'm looking at this versus high and low performance, maybe I do a box plot. That might help me. And what if I saw in my box plot with low and with high, what if I saw box plots that looked like this? Presumably a high level of performance or high number on performance is good. I might think, it looks like on average the high experienced people do better on performance than the low experienced people. But I don't just stop there. I might run a hypothesis test to see if I can prove that, right? So in this one, I would write my hypothesis test. My hypothesis test, let's suppose I wanted to test average performance, okay? And if I wanted to test average performance, what would that be? What would be my hypothesis? What would be my null versus my alternative? Let's see if we can have somebody say, so Michael, or Mike, you want to take a stab at that? What would be my null hypothesis if I want to test the average performance. I wonder if the averages are different.
I'm sorry, I had a chip in my mouth. I'm trying to remember the symbols here. So is the mu?
It is. It's mu, and it should be mnemonic, most of them. So mean goes with mu. So that's the thing.
Yep.
So
And then it's equal to.
okay.
Yeah.
So it's I low is equal to high. Or low.
And then
Go ahead. Sorry.
same thing with the not equals.
Excellent. And there's a not equal sign in there. Right. So let's suppose that we ran this now, and we got data. Thank you, Mike. And let's suppose that we ran this now, and we got data. And of course, when we get data, when we run a hypothesis test, what's the key thing that we're looking at? There's a key measure that we're looking at. Anybody remember what that was? It starts with a P.
What? The p-value.
The p-value, yeah, that wasn't too tough. And so let's suppose, Steve, that we had a p-value, and the p-value was 0.007. What would that mean?
We would say it's. We would say it's not significant because we're looking for p-values higher than 0.05. I remember.
Okay, so think about this. Remember the phrase. What was the phrase that we learned last time? If p
It's low, it's got to go.
if p is low, what goes? If p is low,
HO.
HO must go.
HO.
Right, so in this one, we say we reject the notion that they are equal in favor of the fact that they are unequal. So this difference here that we see is statistically significant. So it's real. What we see is real. That's a hard one to remember, okay? The tendency is to look for high p-values, but we're looking for low p-values. Low p-values indicate there really is something there. There's really fire to the smoke. So low p-values really work there, okay? Another way of thinking of it, and it's not exactly correct, and that's why my statistics advisor is going to roll over in his grave, but it's the p-value is kind of like the probability that the null hypothesis is true. If we have a very small p-value, that would mean it's very unlikely that they're equal, right? So we'll reject that notion in the sense that they're unequal. Upshot of this is if we're looking at the box plot or we're looking at a plot to see something, this really says, yes, what we see over here in this plot, this difference, it's real. So that means, what that means in a practical sense is maybe I can do something about it, right? Maybe I can either do something about this experience level, maybe I have a training problem, or maybe I have a transition problem, or you know what, maybe I just need to look at it more deeply. But the point is that it's worth my time to look at it more deeply because there is a real difference between these groups. Okay? Hopefully that makes sense to everybody. Let me give you one other paradigm that works for a lot of people. If you're not getting this, remember we said H0 is the equal, mu1 is equal to mu2 if we're doing means versus not equal, right? We can think of this as, quote, innocent. The person didn't commit the crime. It's a nothing, right? Versus guilty. The way that hypothesis tests work are exactly the way our courts of law work. We assume what until what?
Innocent until proven guilty.
Innocent until proven guilty. So we assume this is true. Remember, this is how it works. We assume this is true. Then we look at the p-value. If the p-value is very small, that means that this is not true. So we reject this in favor of this. This is like data. We use data or evidence, right? Data, evidence, evidence to try and prove this. We don't try and prove innocence. This is assumed. We assume innocence, and then if we have data, we can prove this. Okay, so if we have a p-value of like 0.35, right, which is not low. Low, does anybody remember what our number that we use for is low was?
0.05.
0.05. Okay, that's low. Okay, 1 in 20. 1 in 20 chance is low. And we don't want to leave this up to chance, so we say, you know, there's really only a 1 in 20. Obviously, in the court of law, we want that to be much, much better. But if this is a 1 in 20 chance that this was just due to sampling, well, okay, I can live with that. But if it's greater than that 1 in 20 chance, I really can't live with that. I'm going to have to get more evidence to prove my case. That's kind of how it works. Okay, so let's try one. Let's see if we can do one more example. And this is going to be clearly a canned example. You're going to groan when you realize the pun I just made. Okay, so in this one, oh, hello. In this one, what we're going to do is let's assume that we had 100 people, and you had 100 people, and I think it's 100 people. Let me just check. Indeed, it is. Okay, 100 people, and let's say that 100 people were given a can of Coke and a can of Pepsi. I guess the Pepsi is skinnier. It's Diet Pepsi. Okay, so they were given a can of Coke and a can of Pepsi, and they were asked which one they preferred. Okay, let's suppose a priori, before the experiment, Coke said 70% of people prefer Coke over Pepsi. Okay, let's see if we can test out this to see if it's true, or to see if this is if we can accept this claim, or if we have evidence to support this claim, or if we don't. So in this case, first of all, do we have in this case we have a proportion, right? So I'm going to use pi, and our null hypothesis is going to be, well, let's hold off for just a moment, and let's just draw our box. And I have a bunch of people coming in here, and I have their preference, right? What type of a variable is this? Num or cat?
Looks like cat.
It's a cat. There you go. Now we could treat it as num, and we're going to find that it's not very much different, but sure does look like a cat. So let's go ahead and try this. First of all, we're going to just do a one cat analysis. So I'm going to go up to Excel stats. Whoops, I'm going to choose this. Excel stats, one cat. Now we didn't do one cat, one proportion last time, but it works basically the same. So here it is right here, and so before we do the hypothesis test, what's your gut feel about do people prefer Coke over Pepsi?
Are we assuming one is they do?
One is that they do, yes.
I mean, the simple math, I would guess that 57% do, so it's not the 70%.
Okay, so there's a couple of different questions here. So let's start out with the first one. The first one was, what's your gut reaction in terms of do people prefer Coke over Pepsi?
Outside of data, I would say that 50-50.
Okay, 50-50, and now let's look at the data and answer that question. I think you've already said it, but I kind of want you to say it more definitively without mixing in the second question.
So the data shows that 57% of people prefer Coke.
So here's the point. So it certainly looks like it's true, right? Now the leap that you just made, and that people make it a lot of times, is that this sample represents the group, right? Represents the larger population. 57% of people prefer Coke. That's not the same as saying 50% of this sample, of these 100 people that we took, right? So what we really want to do is we want to make a statement about the population, but the question is, can we do that? What's the margin of error on this? We don't know. So we can use a hypothesis test to essentially help us with that, if that makes any sense. Hopefully it does. So if we go back to this, I'm going to erase all this here. And if we go to our plot, our PGA. We've just done the I wonder, and now we've done the graph, and it certainly looks like there's a difference here. Let's do a hypothesis test to see whether this difference is real. Okay, so on this one, it would be the proportion that I'll just call it proportion C is equal to 50% versus the alternative that it's not equal to 50%. Now we'll test the 70% one in just a second, but I wanted to illustrate this one first. Okay, so let's go ahead and do this then, and let's see if we can nail that down. So we'll go to tests, and here's our null hypothesis. There it is right there. Pi is equal to 0.5 versus it's not, and it says the p-value is 0.16. So what do we think we can? So I guess let's go back to this hypothesis test. See if I can just put that up. Yeah, right here. So our p-value is equal to 0.16. So what does this tell us about these two? What should we do here? Should we say that this difference is real?
I would say it's not real.
It's not real, so we probably need more evidence. It looks like it's leaning toward Koch, but we cannot reject the null. Does that make sense? Hopefully that makes sense. It's not statistically significant. What might be an action that you could take coming out of that? So here is not significant. Oops, not significant. So what might, oh, go ahead.
I'd say, I'm trying to remember the exercise, but run your model to see if the sample size is large enough.
Okay, so we already know it's not large enough, right? We already know it's not large enough to tell a difference. How do we know that? Because we have the data, and we just did a hypothesis test. So we don't have to go back and see, hey, did I have enough data? We know we don't. So what we might do is we might go back and do one of those sample size calculations to see, how much data would we need, or how much data should we expect? Or we could just say, let's collect a little more data. If we collected another 100 points or so, maybe that would tell us something. Another reaction might be, this question really isn't all that important to answer, so let's just stop right now. We don't need any more data. We just don't have a lot of evidence to say that Coke is more important than, or is more preferred than Pepsi, and we can stop right there. Does that make sense? Hopefully that makes sense. There's all sorts of different actions you can come out with this, but one thing that you shouldn't come out with this is a definitive statement that, well, it's very clear that in the population that people prefer Coke over Pepsi. That's what you shouldn't say. Okay, let's now for the moment go to the second question. And the reason why I wanted to go to the second question is that it's going to illustrate something here. The second question was, Coke claims that 70% of people prefer Coke over Pepsi. Now it seems on the face of it that that's got to be just a bald-faced lie, but as we'll see in just a second, now I'm talking about the flip side of a hypothesis test. To make some sort of claim about whether or not a percentage is included within something is based on is a confidence interval. So to do that, what I did was I chose the people that prefer Coke. You see that right there. And now I'm looking at the confidence interval, and it says that the confidence interval, that means where the true percentage is, lies somewhere between 47% and 67%. So the true proportion lies somewhere in there. It looks like Coke is full of it if they're claiming 70%. We're not getting that within our sample. We're not getting that within the confidence interval. And I also wanted to illustrate this. Notice that 50% is included in both of these, and that's one of the clues as to why this right here is greater than 0.05. Let's change the just to drive home the point here. Let's change let's change this to, what if we said instead of 50%, What if Coke? What if we were interested for? I don't know why we'd be interested in it, but what if we said 47%? Now I'm just using the data here to drive me on this. What if we said, is it 47% versus not equal 47%? Seems like a stupid question, and it is, but I want to illustrate a point here. Notice that 47% is just outside of the confidence interval. And now watch what happens when I put in 0.47. Watch that p-value, 0.47, just under 0.5. You see that? So they're related to each other. If the null is inside, I got to change this to 0.47. There we go. If it's just inside this, it will not reject 0.4. Let's make it 0.472 again to drive home this point. I guess it's not exactly true, but it's darn close. 0.73. How about that? There you go. 0.473, and it basically, if it's inside this confidence interval, that means that you can't. That means there's an equivalence to these two things. All right. So hopefully that hopefully this example, if we go back to 50%, really drives that home. We really can't say with respect to the 50% there that in respect to our sample that we haven't we haven't proven guilty, right? We haven't proven it. All right. I'm going to stop on this one at this point and just ask, are there any other questions that you have about hypothesis tests? Hypothesis test. It does take a little while to sink in. It definitely takes a little while to sink in. So again, what you do is you take whatever your question is. You have your PGA, right? You've made your graph, and you say, aha, two averages, I'm just do the most important one. Two averages look different. Ugh, AVG look different. Whatever that is, whether it's your box plot or whether you've got two different histograms, you know, and it looks like, yep, they're different. It's the two averages. You write your hypothesis test, always with innocent being first. Innocent is, let's call this mu2 and this mu1. Innocent is always equal. There's nothing different about them. Seems weird that we would do it this way, and our alternative is that they're different. And you look for the p-value. Is it less than 0.05? And you use the phrase, if p is low, HO must go. Be careful with that one. I've had some people get out of hand on that phrase. All right. And that's it. And this helps you substantiate whether statistically significant or not. That's a scientific phrase. The phrase I like to use is whether I see what I've seen in the plot is real. Whether I see in my table of numbers is real. Okay. Let us, as the rabbit said, get to where we're going today. So let's start out by going into week 5. We're going to go over just a couple of precepts about modeling. Remember, I said we're going to talk about modeling, and I have a lot of passion for models, and so we're going to be starting at, I think it's slide 47. Yes, 47. So I have a lot of passion for this, and obviously it's a big thing in today's business. Using big data has opened up a lot of these techniques to what was not available before. And models can be very, very powerful, but they can also be a little bit dangerous. So we're going to go through this pretty quickly, but I just want to give you a smattering of what the various techniques are, and maybe one or two things to look at, to look after. This is really just general knowledge for Six Sigma. So let's first talk about some concepts, issues, and uses. Now, we've all built models before, Models could be anything. There are environmental models, there's engineering models, there's model airplanes, simulation models. What we're talking about here is a mathematical model. And what we can use for this is we can we can essentially use these models to predict the future. Now, anytime we make predictions, I think it was Yogi Berra who said it's really difficult to make predictions, especially about the future. It's much easier to make predictions about the past. But it's worth it because when we can do it, we can certainly make our lives a little bit easier. All right. There are all sorts of things that you can predict. You can play what-if scenarios very quickly with a math model. You can look at optimal performance, quantify relationships, to inputs to outputs. Now, one thing I always tell every black belt that I talk to and teach modeling to, or any modeling to, is that you've got to always remember that all models are just models. They're all wrong, okay? All models are ultimately incorrect. Even the best physical models that we have, you've seen the equations E equals mc squared and F equals ma. Those are both technically incorrect models. They don't work at the minutest details. However, they're both extremely useful, and that's why we use them, okay? So models are never correct. They're only useful, or powerful is another good word that you can use. So we can talk about a more powerful model or a more useful model, but we can't usually talk about whether a model is right or wrong, okay? Back in the day when I was building hurricane models, it was very clear that the president of the company that I worked for, she often got confused about what was real and what was a model. She would often get very upset when her model, when the data didn't fit the model, and she would work very hard to explain why the data were wrong and not why the model was wrong. So I understand that very, very well. I've been caught in that trap before. So anyway, I think you get the picture. I'll get off my soapbox now. Okay. The other thing I wanted to point out is that mathematicians and engineers often get the rap for being not very creative people. Modeling is a very, very creative process, as I think I'll hopefully be able to give you a flavor of today, and then certainly on Friday when we cover more of this. It can drive different uses, both in the building of a model as predictive, and also once you've built a decent model, to use that model creatively to suggest different things that you could do to your business or with your business. Very, very valuable. Okay. Last thing I want to talk about before, or maybe not, I guess this is the penultimate thing I want to talk about before, before we get into the specific techniques, is that we want to take a walk before we run approach to modeling. Now that's going to be true in the course, but it's also going to be true, I want to suggest that it should be true when you do any modeling work as well. Start by building simple models and then refine those simple models to make them more complex where you need to. Don't start out with a super complex model and then live with it. A lot of times you create a lot of clutter, and that clutter is hard to take along for the ride to be able to use creatively. And it's also kind of dangerous too. That you can do things like overfit. We'll talk a little bit about overfitting in the next couple days, but not too much. Okay, and this is part and parcel with that is also something called Occam's razor. Now I'm sure some of you have heard of this. Maybe all of you have heard of it by now. Occam was, I think, William of Occam was I think he was a 13th century or a 14th century writer, and he postulated that essentially, given two things that explain something equally well, we should choose the simplest. Now, a lot of people misinterpret that to saying a simpler model is always correct. That is not true. A simple model is not as good as a complicated model if the complicated model does a lot better job of predicting. So both of the things have to be roughly equal in predictive power, and if both things are equal in predictive power, we should choose the simplest. That's Occam's razor. We don't have to go with that, but it's often a nice way of thinking about it. Okay, this is an example of what we're going to do before, or what we're going to do before. What we're going to do at the end of today's lecture, come on, is if you look at this particular model is for a y, whatever y is. It could be performance of a person. This one has it has a bunch of different terms in it. It has an x squared and an x cubed. My goodness, this is a fairly complex model. And it has something that's called an r squared adjusted. We won't know what that, we'll know what that is by the end of today, which is 93.1%. This is kind of like a figure of merit. How good is this regression model? This is a regression model. How good is it? Here's another model, 92.7, almost equally good, but this only has one term in it. It doesn't have the x squared and the x squared. Much simpler model. Generally, I should put in here a big caveat. Generally, we should prefer the second model because it explains the behavior of y about as well, but it's much easier to use and more and understand. There's an overused word here, robust. Also, I'm going to use that in our course. Robust means essentially it's just a lot harder to break this model. It's harder to misuse it. It's harder to break it. It's easier to break this. There's a lot more constraints on it. All right. And that should cover Occam's razor pretty well for now. Well enough for now, I think. Okay. Whoops. All right. Now, because models predict future behavior by looking at past, they can produce some problems, or they can come with some problems. Models are not usually great when you look at an extremely quick changing situation. So that's a problem. Sometimes, and so that's one of them. Another problem is, I alluded to before, is overfitting. If we throw everything in the kitchen sink in, that can hurt our robustness of a model. It can make it easier to break. It can put more assumptions on it. So again, generally, we should prefer things that are equal in explaining power, but are simpler. We should prefer the simpler models when they're equal in explaining power. The last one I wanted to mention is something called cause and effect, and we've heard this. I just want to give you one example of this. You've heard the phrase causation. Correlation does not imply causation. We're going to run into a couple of those examples. I want to just show this. So here's one where suppose I got some data and the scatter plot looked like this, and we're going to learn how to interpret this, but it certainly looks like there's a relationship between the input and the output, whatever those are, x and y. It certainly looks as if maybe as the input increases, the output also increases. But I want to be very careful about saying it doesn't cause those two. Historical data often holds lurking variables. For example, what if the example was on my x-axis is ice cream sales, and on my y-axis is drowning deaths? Well, it certainly looks like those two things are correlated. In fact, they are. But we want to be careful about not saying one causes the other. I mean, maybe it does. Maybe mom was right, and you need to wait a full hour after you eat to go swimming, right? But seriously, what's probably driving this is weather, right? So when it's warmer weather, people eat more ice cream, and they also drown more because they're swimming more. So things can be correlated with each other if there are other lurking variables that we don't know about. Examples of this are just all over the place. We do have a technique that's going to help us nail if we really have a cause, and we can do that, and it's called design experiments. And we'll be starting to look at that at the end of Friday's lecture, but not yet. Okay, so before we get going in simple linear regression, I just want to talk about a survey of the techniques that we're going to use so that when you see them later, you'll understand what they are. First things first, we'll talk very briefly about transformations. Okay, so here's an example of something that you might want to use a transformation for. If we're using a regression, and I want to regress, for example, I want to look at assets and see if I can break a company's assets by looking at their sales. I might want to do that, but you see how this is there's a huge fan that's going on right here. That kind of gives me a clue to maybe how to look at those individual points And yeah, you see how some of those are really driven by outliers? A transformation, and we're only really going to focus on one. It's by far the most important one. It's the log transformation, a logarithm. When we transform this with a log, we essentially take this and make it look like a normal distribution, and take this and make it look like a normal distribution, a bell curve. Okay, that's what a transformation does, and it helps make the regression more robust. So if we had fit a line here, for example, you can see how there's a lot of problems with this. And we're highly relying on one data point really to tell us what that slope of the line is. Not very robust. So we'll cover transformations very, very briefly on Friday. Okay. Polynomial regression. Sometimes I'll have a regression, but my scatter plot will look like a curve. So polynomials might help me there. Polynomials can model a curve a little bit better than a straight line. Multiple regression. Sometimes maybe I'll have more than one variable that I want to add into the equation. That should be self-evident that that's a powerful technique that we'll want to know. And dummy variables. Maybe sometimes I might want to have a cat, and this is really categorical. These are cat variables. I think it was Mike who said that. Cat variable. What happens if I have a cat variable that I want to add into the model? I can do that using dummy variables. Okay, so we'll learn that technique as well. And finally, yes, it's another way of building a model, design of experiments. You may have heard of this as the very common one today is something called A/B testing. A/B testing is or some people call it champion. There's another one called champion-challenger process. These are both examples of a very simple type of design of experiment. We're going to learn that, but the key thing about design of experiments is you can show cause and effect. The difference between regression and design of experiments, I'll say it now. It's like Hans and Franz. Say it now, hear me now, and believe me later. I'll say it now, and you can hear it later as well, but DOE models are proactive. Proactive. You're actually jiggling the parameters. You're actually fussing with the buttons to see what happens. You're running an experiment. Regression models tend to be data that's just collected over time, and it's in the past. So design of experiments can often be very powerful in that way. Okay. There'll be, I don't know if we'll use any lecture time to talk about time series models, but there's certainly a video that will do this. This is definitely an advanced technique, and it gets into real forecasting and adjusting for trends and things like that. Trends and seasonal adjustments and serial dependence, and all sorts of stuff like that. If time permits, we'll cover that in the final week, but chances are we'll have a video and we can discuss that, and certainly I would encourage you, if you have any issues with any problems or any things that you want to do with time series models, forecasting, certainly open to talking about that. All right, so we covered a lot of ground in here. Let's get started on the very simplest of the regression, and we'll start again with the walk before we run. Take a minute to write down, in your view, what are the key takeaways of what we just talked about, what are the questions that you can answer, and how you can support business improvement. Just actually, if you focus on that first one, the key takeaways, I think you'll be good. And then we're going to cover everything in simple regression in workshop fashion. So we're not going to be going through slides except for maybe showing you just a couple of slides. Okay? So just take a minute to write in that, and we will be we'll be ready to start on simple regression. Okay. All right. Well, let's, like I said, I'd like to kind of cover this in sort of workshop fashion. So we're going to be starting out by covering what's in the slides, or in the book, slides, I think, 2 through 46 or 47. Yeah, slides 2 through 46. So when you want to go back and look it over, the examples that we're covering are covered in there in pretty big detail. But let's start out by just talking about, we're talking about regression, and I want to just talk through sort of what are the things that we want to talk about first. So we're going to talk about three things. One is a scatter plot, okay, which is our graph, and then we have a couple of different calculations. One is common in the vernacular, and that's correlation. Okay, so correlation is something that you hear a lot. We're going to show you what the calculation is for correlation, but more importantly, we're going to be talking about building a regression model. Okay, so here's what's coming. We're going to be doing all of this stuff. The setting is I have a y and I have an x, and my y is a num and my x is a num. Okay, so my output is a num and my input is a num. So before we get started, you know the drill. I want you to draw the box, and let me give you an example so that we can go off this one. Let's suppose I measured a person's performance on the job. Okay, and let's suppose I also measured their experience level in years. Okay, that would be a number, and this would be a number, and this would be perfect for the setting of at least starting out with looking at a scatter plot. Okay, so I want you to take a moment and come up with your own example. Could be for your project, could be the time that it takes for me to make an appointment, or a physician appointment, or it could be the time that it takes, or the number of loans that I processed in a day, or it could be the time that it takes me to produce an optical table. Okay, so take a minute to write those down, and let's get a couple of examples. Give me a heads up when you're all set.
Mark, it's Regina. I would say number of years as a processor and number of insurance defects.
Insurance defects. Okay. Okay, that'll certainly work for this if you're thinking that way. How about another example? Thank you, Gina. Let's see, John, do you have an example?
Sure. Education level and salary.
Okay, which one is the X and which one is the Y?
Education level is the X.
Got it.
Y is salary.
Okay, excellent. So that certainly will work as well. And I like how you guys are coming up with examples where I think in a lot of cases, let's take the second one, right? Salary versus education level. This could either be a cat or a num. It sort of depends on how you collect the data, right? If you collect it like 1 through 12 or 1 through 16 or whatever that number is, then it's kind of a number. If you collect it as high, medium, low, it may be a cat. All right, excellent. So if you're still having trouble to do that, come up with an example, use the examples that we'll cover in class, or come up with your own example from real life, like the time it takes for the pizza guy to deliver to my house versus the miles I am away from the pizza place, or something like that. Okay? All right. Okay, so that's kind of the background for this. Let's see, one other thing here before we go into these examples. Just to put this in context, again, as Steve said, it's after we've already collected some data, and it's essentially the G here. We'll start it with the I wonder. The G is our scatter plot, okay? And our A is going to be our model, our regression model. And also the correlation, I guess, to a smaller sense, the correlation. And yes, there is a hypothesis test associated with this. It's kind of a boring hypothesis test, but it is what it is. Okay, so in building the regression model, we'll also walk through a couple of different things. We'll walk through the fit. We'll walk through the something called R squared. This is really how strong the regression is. And we'll look at something called the residuals, which is really how safe the regression is. Okay, that's supposed to be 3. And then finally, we'll look at how to predict with these regression models. So when we get to regression, which we will very soon, we'll want to do it a little bit more circumspect than just say, hey, what's the line? And now I'll go fitting a bunch of numbers. Okay, we'll make sure that it's safe to do so first. Okay, so let's go, let's start out with an example. And what I want to do is we'll look at mileage versus speed. Okay, so here, this might be in a track test where I'm checking to see I wonder if the gas mileage that I get in my car is affected by the speed that I drive. Okay, so let's start out with that. The first thing that we should do is do a plot. Okay, and in this case, it's a scatter plot. So let's take a moment to do a scatter plot first. Now, of course, the beautiful thing in Excel Stats is it's all going to be there for us. So all we really have to do here is select the data and click on ToNum. And let's take a look at that scatter plot. Here it is. I know it's a real exciting one. And this is kind of the thing that the way that I first look at a scatter plot. I start out by saying, are there any outliers? So I don't see, I'll just, whoops. I'm just going to walk through this myself first. I start out by saying, are there any outliers? Now, I don't see any outliers here. If I saw something here, I'd say, hey, that's an outlier. Gotta check it out. Outlier. Okay, my interpretation of an outlier. Okay. Okay, so if I saw an outlier, I'd check it out. Here, I don't see any outliers. Okay, the second thing I'm looking at is I look at sort of the shape, and I look at the strength. So in this case, I see, here's the shape that I'm seeing. I see a line, and it looks pretty strong because when I optically draw that line, and I usually just draw it in my mind's eye without the pen, I'm looking at the scatter of the, and this is why it's called a scatter plot, I'm looking at how close those dots are to that line. If they're very close, then that's a very strong relationship. And then finally, I'm looking at the direction. And the way I do that, in this case, I understand that it's negative, because as speed increases, gas mileage, my response that I care about, decreases. So I can say essentially, as speed increases, gas mileage tends to decrease. That's it for a scatter plot, folks. Not too much to it, but you want to take a little bit of time to do all those things before you go ahead and just draw the line. Because once you draw a line, you only see the line. And once you fit an equation, you only see that equation. Somehow those things become very real. So I like to do those things before I do that, just to give me an idea of what I see or I don't see. Okay? All that makes sense? Okay, let's try out a couple of examples, and let's see how we do. So let's see, AQI. So in this case, I've got a bunch of cities in Australia, and I'm testing to see the air quality index. I want to see if air quality is if the distance from the nearest city, or the distance from the city, if air quality can be explained by that. Okay, so let's see if we can do a 2-num analysis on that. So let's go ahead and do that. I'm going to replace this. Oops, I didn't close it down. I'm going to be smarter. There we go. Try this again. All right. Now the first thing I want to do is I want to make sure I have on the x-axis the right thing. So let me go ahead and move that around. Okay, so let's talk through this scatter plot. So let's see. Dan, can you talk us through the scatter plot, what you see here?
So this tells me that the distance from the city, as it increases, the air quality does appear to get better.
Okay, great. So a big summary at the end. Now let's walk through the individual pieces. Outliers, right? Always the first thing that you want to look at. Do you see any things that you'd want to check out, maybe look a little more deeply into?
I think the data point farthest to the right.
Maybe this guy right here?
Yep.
Yeah, I agree. It looks like maybe I'd check that out. I guess going back to the question, another question I want to ask is, what shape do you see? What kind of form or shape do you see in this data?
It's a positive slope.
Definitely a positive slope. Do you see a line? Do you see a curve? Do you see?
You know, for some reason, I actually see a little bit of a curve.
Yeah, I do too. And I think this is one of the reasons why I want to ask the question about the outlier first, is because, oops, let me erase that, is because if you checked out this point, you found out that this point was somewhat anomalous, maybe there's not really a curve, maybe it's basically a line. Yeah. On the other hand, if this is really part of a trend, maybe you do have, oops, and this is a horrible drawing, but maybe it looks more like this, and maybe it's more of a curve. So that's why it's kind of imperative to ask the question about outliers first. But generally speaking, you got it for sure. The longer the distance from the city, the higher the air quality index. Presumably that's better. Okay, excellent. Thank you, Dan. Let's try another one. Okay, let's try another one here. Let's try baseball attendance. Let's try this one. Okay, so here I've got advertising spend, and I've got the attendance in thousands of dollars. So in this case, my output is attendance, and advertising spend was the previous week. So we want to study what effect does the dollars that I spend in advertising have on attendance. So again, I have 2-num analysis, and I want to make sure I get the output and input right. There we go. And let's see, Gina, can I ask you for help on this one?
Sure. It looks like as far as outliers, I don't see any. It looks to be a curve and positive.
Good. All right, good. And you know, just going through that in your brain is really going to, I mean, if you were going to describe this to somebody now, and we're going to have a different model that will look at this, but how would you, if you were the person in charge of the advertising dollars or the attendance, how would you describe this to somebody who who was asking you the question, how much should we spend on advertising? How would you describe it?
I would say you
Oh, go ahead, Steve. I think a few people were saying.
I would say, what about 30,000? You start getting no good effect on your spending. It's actually showing that the attendance goes down. So if you want to maximize your spend, about 30 or so would be the cutoff.
Good. I mean, there's lots of different ways you could say it, but again, knowing that curve and understanding that this translates into something real, to say, there's benefit to spending money up to around, I don't know, wherever that is, 25 or 30,000, but after that, it's not worth it. And in fact, it may even be counterproductive. It may actually decrease attendance. I'm not sure why that would be, but that's what the data are saying, is that there's really a limit to how much this spending is going to help us. So, I mean, it can really inform a decision, and that's the best that you can hope data can do. All right. Okay. We'll do one more. Let's see. Let's do one more. Okay. And, oh, great. Let's see. I want to do, serves me right for labeling my stuff. This is just generic stuff, right? Y for all that. Let's see if I did this right. There we go. Okay, let's try this one. Suppose this was let's leave it generic, and let's call it Y, just call it Y and X. So let's see. So John, how would you describe the relationship between Y and X here?
As Y increases, X decreases. So it's, I guess, an inverse relationship.
Got it. I'm going to ask that question differently. I'm going to ask a better question. Help me interpret this scatter plot. What do you see in this scatter plot?
I see one outlier.
Okay, good. Basically, that's the one thing I wanted to say. If you don't see the outlier in this one, you're not looking for it.
Oh.
Right? That's right. We all see it now. So if you don't take this outlier into account, you're really not doing your job. You got to do that. That's the most important, because but the rest of it, once we remove that, it looks like there's a relationship between these two. And who knows why this is the way it is. It could be just a data error, but it could also really tell us something very different about the process or about what we're doing. Outliers are often very, I think I've used the phrase before, pregnant with information. All right, that's all. That's basically it on scatter plots, guys. Not a heck of a lot of a trick to it. The trick is just doing it a few times, recognizing those patterns, and learn to talk to your plots. I guess what was that, Fran Drescher or whatever in the 80s and 90s always used to say, talk to the hand, talk to your plot. You can do it with the door closed so nobody hears you, but once upon a time I played an awful lot of chess when I was in graduate school, wasted a lot of my time, but I knew a number of the top 10 players in the U.S., and one of them was a decent friend of mine, lived in Columbus. And he told me the biggest piece of advice he would give me is to talk to my pieces. I said, what are you talking about? He said, no, develop a dialogue so that they start to become players in your play, and you start to manipulate those puppets a lot better and understand what's going on. If you can language what's going on in your plots, you're going to be able to communicate that to people better, and your creativity is going to go way up too. Alrighty, let's move on to the second piece, which is correlation. And to do that, I'm going to go back to our mileage versus speed. I'm going to close the Coke versus Pepsi because we don't need that one anymore. I'm going to go back to the mileage versus speed, and we already did a scatter plot, and we found that this was that it certainly looked like it was a line, and it was a negative line. Okay. So to do the correlation, all we have to do, what correlation is it's a calculation that quantifies the strength of this line, and it quantifies it between, I always forget to erase my stuff, it quantifies it between -1 and +1, okay? So -1 means extremely strong negative. Means strong negative relationship. Okay, this, for example, is going to be close to -1, as we'll see in a moment, because it's got a very strong negative relationship. This means strong positive +1, strong strong positive, and 0 essentially means no relationship. Okay? Want to emphasize it's always very important to look at the plot first. If you just look at the correlation coefficient, you know what, let's just look at the correlation coefficient first, and then I'll get on my soapbox. So to do that, let's look up here, and we can see that there's a correlation that says that it's minus 0.969. So that's definitely, if we're looking on the number line between -1 and +1, it's like it's like almost exactly on -1. So this is an extremely strong negative correlation between these two. Okay, and that just means as one, excuse me, as one increases, the other decreases. That's all that correlation means. Okay, so it's just a quantification of how strong is strong. All right, let's take a look at another one. Let's take a look at the air quality one. So I'm going to close this down, and we'll look at the air quality. Whoops, hello. Where is it? There. We'll look at air quality, and we'll do the same thing with the correlation here. And remember, I've got to switch those variables around because I've got them in the wrong order in my spreadsheet. No problem. So this is air quality versus distance. We can look at the correlation. Strong, but not as strong, right? So this is 0.78. Okay. Let's try one more, and I'm going to have you guys guess. So let's see if I can find it. Service and capacity, part 2. Hello. Yeah, I guess we'll use service and capacity, part 2. All right. I don't know if this is going to work. It didn't work last time. Yeah. Oh, it did. Okay, so people hours versus experience. Okay, I want to make sure whoops. I'm going to look at service level versus people hours. Okay, so hold on. All right, here's service level versus people hours. I wanted to hide it from you so you can guess. So service level versus people hours. And I'm just going to zoom in a little bit so we can see it a little better. Format the axis, and let's just go between 50% and 100%. There we go. All right, what correlation would you guess on this one? I want you to write down your guess instead of saying it out, but just take 10 seconds and guess on the correlation. Somewhere between -1 and +1. Okay, hopefully everybody's got a guess. Let's see. Mike, would you like to volunteer your guess? I always pick on Mike for the hard questions.
I think it's close to 0.
Close to 0. Okay. Let me walk you through the scatter plot. Okay. Number 1, outliers.
It's hard to see a direction. I mean, there's outliers all over the place.
Okay.
There's no tight grouping anywhere.
Okay.
I mean, I see one to the bottom, top right.
Got it. Got it. So, yeah, if you're not seeing any relationship between these, do you see a relationship between these, a form?
I mean, there's a slight one from bottom left to top right, but
looks like there's maybe something like this.
Yeah, I mean,
Yeah.
if you go with that, then there's a lot of outliers in top and bottom of it.
Yeah. Okay. Got it. Like maybe this one and maybe these, so forth.
Yeah.
Okay. Got it. So let's see where your intuition was. So yeah. Okay. So 0.27. Oh, I'm sorry. 0.5. That's interesting. So it's probably a lot. Correlation is a lot stronger in a lot of cases than we think. But what we'll find out is that a correlation of 0.5 isn't all that impressive. As you're probably seeing right here, my guess is that nobody in this class would look at this and say, I'm willing to put my reputation on the line to say, if we have this many people, we're going to get this service level. My guess is that very few people would be willing to make that prediction. And that comes out by something that we'll find out later is the predictive power, which is kind of evidenced by this thing that's called R squared. So we'll get into that just as we started. Okay, so if you didn't get that one, don't worry about it. Building up intuition on correlation is difficult, and you know what? It's not all that important. You can just look up here to take the note of that correlation. The more important thing is going to be in terms of building the model. Okay? Correlation is really just in here to say, you know, we're going to cover correlation because it's in the vernacular, and so now you've got it. One other thing I want to mention before we cover correlation, or before we cover modeling, is the following. Let me just erase this. Good. And go back to my whiteboard. All right, I'm going to make a hypothetical relationship between two variables, x and y, whatever they are. And let's say that I got a pattern, or I got a plot when I looked at my scatter plot, and it looked like this. Don't ask me how I could have gotten this, but I'm exaggerating this to make a point. Okay, so do you see a relationship between x and y? It's not a trick question. The answer, I think, is yes. Yeah, there seems to be some circular relationship or something like this. You certainly see a relationship here. But anybody want to guess what the correlation would be? Identically 0.
Wow.
Yeah, it turns out there's no correlation. Why? It's because correlation means linear correlation. So just because something doesn't have a linear correlation, this is another reason why I don't want to just rely on a correlation coefficient. Just because there's no linear correlation does not mean there's not a pattern. So for example, in a more realistic one, our baseball attendance one, which looked like this, remember? And it was pretty convincing to us. I think we all saw this. It was a pretty convincing pattern. This is not going to have a correlation of like 0.9, even though there's a very strong relationship. So that's one of the reasons I like to mosey on down into the models, because models are going to capture these sorts of things. Now we are going to start with the linear model and learn as much as we can about it. But next time, I promise, on Friday, we'll cover how to handle stuff like this. Okay? So I just want to mention that in passing before we go to modeling. We are, however, going to start out with a situation where we're modeling an x and y with patterns that are pretty stable, that are pretty standard, stuff that looks like this. Okay? So let's get into the simple linear regression. And to do that, again, I'd like to go back to our gas mileage versus speed example. Okay, so let's go ahead and do this one again. And we did the scatter plot, and we looked at the correlation. We said, yeah, there's a strong line here. There's strong evidence of correlation. How do we fit the best line? All right, well, the answer in this case is really simply, we just click on the draw line button and we click on the show equation. All right, so while that was a really simple answer, it's not a very appealing answer because anybody can do that. I think it's kind of nice that it does this, but let's look at a couple of other things before we make predictions from this line. Like, for example, we might predict, I'm jumping ahead a little bit, but we might ask the question, what would happen if I were driving 70 miles an hour? What gas mileage would I expect to get? And what I could do is I could just, I keep doing that. Gotta stop it. I could do, just start on my 70 right there, go up to here, go across. I'm trying to draw a straight line and say, looks like I'd get about 18 miles per gallon if I drove that speed. Now that may or may not be a good thing to do. What we're going to do before we go ahead and make predictions is spend a little bit of time analyzing to see if it makes sense to do so. Okay? So to do that, there's three different parts. Those three different parts are, go back to this again. Hello. Before we do that, we're going to look at the fit. We're going to look at the R squared, and we're going to look at something called the residuals. Now, it's all going to seem silly when we only have two variables. All this is going to seem silly, but when we have multiple variables, we're going to start to see, oh, I can't just look at all this on a plot. I'm going to have to do a few extra things before I go ahead and do this. So that's why we're doing it the safe way. But we'll go ahead and do this for this example, for mileage versus speed. So let's go ahead and do it. So instead of just using this equation, we're going to go through a couple of checks first. So these checks are going to be on the next page right here, correlation and linear regression. Let's first look at the fit. The fit, and this hopefully isn't going to give you fits. Keep doing that. All right. The fit is basically saying I have y. What it just did was it fit y equals b0 plus b1x. Okay? It came up with numbers for b0 and b1. Okay? In fact, it came up with the two numbers, 47.46. This one's 47.46. And this, see that there? It says intercept, and this says estimate. Slope estimate. It came up with this as 0.41, whoops, minus, that's our negative, right? There's our negative, minus 0.411. Okay? So essentially that says for every mile per hour I go faster, I lose about 0.4 of a gallon per hour, or per a mile per gallon. That's what that says. Okay, so the fits that we look at first are these, and the way we look at the fits is, believe it or not, we look at either these pictures right here or the p-values. So p-values are testing the following. These things right here are tests. See, that's a hypothesis test. That's a hypothesis test of, I'm just going to draw it for this one right here, because this is the more important one. H0 is my slope equal to 0 versus not equal to 0. That's my H1. Okay, slope not equal to 0. We can see, whoops, there's my slope, right? So that's that one. Slope equals to 0 versus not. We can see the p is very low, so we reject the null that the slope is equal to 0. In other words, this is this model, this term, we should keep it. Okay? That's all we're saying. If this is really low, we keep the term in our model. That's what it means. Now, this isn't going to mean anything to us right now. Of course we keep the term in a model. The line is better than nothing. That's what this is saying for this. Again, in multiple regression, this is going to be more important. So hang on to your, suspend your disbeliefs and just realize that you're going to have to look at the p-values to see whether or not to keep the terms in the model. Now, by convention, you're in luck. By convention, we quote, always keep the intercept. We always keep this one. I don't know why I didn't scare quote both of them, but we always keep the B0. We sometimes keep the slope if it's significant, okay? So we're going to find out sometimes that the intercept, what the intercept is the following. If, erase this all, if I extended my line all the way till it crossed the axis, that's my B0. That's my B0, okay? And the B1 is my, if this is Y and this is X, it's my, that's why they call it the slope. It's Y over X, okay? So that's what it is. It's the change in y as you change x. That's my B1. Okay, now we didn't have to know any of that to click the button. Oh, I'm sorry, was there a question? Sorry. All right, I'll keep going. Anyway, so that's what those things are. Generally speaking, we always keep this. We keep this when it makes sense for us to do that. All right. So, like I said, this is going to be much more. This is going to make much more sense when we do multiple regression, which is coming right up. Okay, let us, as the rabbit said, finish by looking at the next two things, which are the strength, which comes from r squared, and the residuals. Okay, so the strength, like I said, comes from something called r squared, and r squared is a figure of merit that tells you something similar to the correlation coefficient. Okay. Generally speaking, the interpretation is how much of y is explained, how much of the change in y is explained by x. So in other words, I can say if this were gas mileage, I solved about 93% of the problem of predicting gas mileage if now I just understand why people are driving fast or slow. Now, by the way, this is not real data. This is fictitious data. But that would be a heck of a model, right? A model that explained 90% of why gas mileage is good or bad. That's pretty good. So good for r squared is going to be like 75, 80% is going to be a really good r squared in most applications. In marketing applications, sometimes 20% r squared is a heck of a lot better than what they have. So they'll take a lift of something like that. But in most applications, like operations, you're going to want like a 60%, 70% to even, sit at the table and really use this, stuff. Okay, so that's the second stop on the train. We look at r squared. So for this one, we'd say that's a good r squared. So this is a pretty good model. The last thing we have to do is check for robustness, right? To see if it's safe to use this. That's residuals. Just to remind you, that's residuals. That's this piece right there. Okay, so fit, that's the p-value. R squared, that's the strength. Residuals is it safe? Okay, let's check it out. Let's see if it's safe. So here's what we do for residuals. Where are they? There it is right there. We click on this button, and it's going to give us a whole battery of things that we look at. Okay, so here's what we really care about. We're going to go to this one, and we're going to look at the residuals versus in this case, the speed versus the predictor. Okay, and we're going to look to see, are there any patterns that we see? Now, here's what we want to see is no patterns whatsoever. Here's an example of no pattern. Okay, and by no pattern, I mean you look at it for like 2-3 seconds, and if something isn't popping out at you, you're moving on. Okay, so this one, for example, no real patterns. Let me give you an idea of the patterns that we're looking for by, instead of me drawing them, let me just show it to you on slide 30. I'm just going to go to it. Here are some patterns that you might look for. Here are some patterns that you might look for. This is a sign of a good regression. There's no patterns whatsoever. I don't see any rhyme or reason to this. Here's an example of a pattern where this basically is going to show I have a poor fit. I need other things to explain it. Maybe I need a polynomial. Maybe I need other variables. But here's a pattern. First it's low, then it's high, then it's low. Here's another thing that can pop up in residuals. Now again, this is all going to be obvious, but it's not all that obvious when we're looking at multiple regression. And here's probably the most significant pattern that you want to look for, and this is called a fan shape. This often shows that your predictions are really good in one area, but they're going to be poor in the other. So you see how this kind of has a shape of sort of a fan that's kind of fanned out there? when you see that, this is the only time that we're even going to think about transformations. This might say transformations, or it might say other variables. But so far, it looks like, at least in our example, we looked at the residuals. They look pretty good. So we're going to move on. Okay. I'm going to shut that one down. So this is an example of something where I have something called the 5-second rule. Right? It has nothing to do with dropping cookies. You look at this and you look at it for 5 seconds, and if you don't see something really popping out at you, you're shutting this down, and you're safe. You're good. You're ready to move on. Okay, so once you've crossed all those different things, then you can go ahead and make predictions. You can either do it in the way that I just did it before, by drawing it and eyeballing it, or Excel Stats has a really nice facility here where you can actually type in a variable. Whoa, that was a, I don't know if I needed that much. You type in a value, and it's going to tell you what, you type in a speed, and it'll tell you what the gas mileage that it predicts would be. So let's try that for 70. It looks like its prediction would be 18. If you drive 70, you get 18 miles a gallon. But it says you could get anywhere between 14.6 and 22.3. Its best guess is 18.6, but if you got anywhere between these two, you shouldn't be too concerned. It's just the brakes. That's kind of how it varies. And you can type in different ones, like 60 or what have you. Okay? And you can do more. There's no limit on that. All right. So that's basically it for doing a regression. And so to kind of complete what we're doing here, I'd like to pause and pause for any questions that you might have. And then we'll do a couple more examples. And then I want to show you the power of multiple regression. And I think that'll really get us going for Friday. We'll be in good shape. So what questions do you have right now about simple regression? Just one X, one Y, trying to fit a line. Okay. Before we move on, we've talked about predictions. Where are ye? Oh, I moved it again. I want to point out one more thing. And this may be obvious to everybody. Well, let's suppose you went through your whole process. You said, I looked at the scatter plot, no outliers, didn't do any checking, looks pretty strong, negative. There's my correlation, looks pretty strong. So I'm going to go ahead and check my fits. Oh, yeah, they're both significant. Yeah, definitely the line makes sense. R squared of 0.94. That's 94%. That's pretty darn strong. Let me check my residuals. Come on, residuals. Looks pretty good. Those residuals look pretty good. I don't see any patterns. So I'm going to go ahead and draw my line. I'll show the equation. I might even plug this in Excel or something like that. And let me go ahead and make some predictions. Okay, so I could predict all over the place, but let me just go to this because it's nice and convenient for me. And I'm going to type in, oh, I want to see my gas mileage if I drive 150 miles an hour. Okay, what's wrong with what I just did?
That you go below 0.
Well, okay, so I got a result that doesn't make any sense, right? So right away you should realize never just blindly plug into things. Well, what did I do right here? Let's look at the original data points that I had. I plugged in a value way outside my range of my study, right? That's called extrapolation. And you want to be very careful whenever you do that, okay? Don't just go in willy-nilly and plug in variables. So I plugged in 150, and man, that was way outside my range. So regression typically is good when you stay inside the range of the data that you have. But when you start going out on a limb, realize that you're going out on a limb. Creating equations have a funny effect on people. Remember what I said about modeling. How many models are right? Answer is 0. You really got to know what's robust, and part of the robustness is knowing what to type in, what to predict. Okay, hopefully that was a decent enough cautionary tale to move on. Let's do our AQI example, and let's see if we can build a model for distance from city and air quality. Okay, let's suppose that we were satisfied with our scatter plot to go on. So let me just kind of walk people through it. So let's see. Let me pick on, let's see, John. So we've got an equation here. Our y equals, and I won't write down the b in the b0, but I'll just write down, actually I'll just write down the symbols b0 plus b1x. Should we keep these terms, either the b0 or the b1? That's the fit. Do you remember how to do the fit?
P-value is small.
Yep.
So yeah.
That's right. So the p-value for both of these is small. Excellent. P-values for both of these is small, so these fits are good. So that gets a check mark, and that gets a check mark. And by the way, this always gets the check mark, right? B0 always gets the check mark. So we're good there. Okay, excellent. Thanks, John. All right, second stop on the train before we go ahead and predict. Let's see. R squared. Steve, how are we doing on R squared?
So 0.78, which is pretty good.
78%. Pretty good. Okay, so I'm willing to maybe make a prediction or two using 78%. That doesn't seem too bad. All right. And now let's see. Let me go down to the residuals. Okay. Hardest one. Gene, I'm going to ask on you. Residuals. What do you think?
5-second rule, right? I would say no pattern.
Wonderful. So that means, is that good or bad?
That's good.
That's good. That means our regression is relatively safe. So we're good with making predictions. All right. So so in other words, we could draw on that line, and we could show the equation. And you know what's interesting? Probably if we had more data, we might see in those residuals, we might see that, and maybe if we took a little bit more time than the 5 seconds, we might have seen these outliers. And we should always do that. But assuming that those outliers are not too bad and we're willing to live with that, what might be the prediction of the air quality? We might want to predict, I don't know, the distance of the city, 150. It looks like that air quality might be whatever that means, 7.1 or something like that. Or if we wanted to quantify that a little bit better, if we lived 150, maybe that's kilometers because it's Australia from the city. Yeah, it'd be 7.36, but you know, it could be anywhere between 5 and almost 10. So the prediction is kind of a wide prediction, but it's not terrible. All right, let's do one more. Let's do the service and capacity one. Oh, I've already got it open, right? Okay, so here, what I've got is we're looking at a situation where we're looking at service level. Maybe it's a call center or something like that, and we're looking at people hours. So I wonder if, the question might be, I wonder if adding people, I wonder if we can come up with a relationship between those two. And I'm just changing the scale here so we can get a better view of it. All right, so let's suppose we've gone through and we said, yeah, we saw this. I see kind of a blob, but let's go ahead and draw that line anyway. And I might even show the equation. But before we go ahead and use it, let's kind of walk through. This. So let's very quickly take a look at the fit. So again, maybe I'll ask Dan. I think you got off last time scot-free. So what do you think of the fit here? Should we keep the terms, our slope and intercept?
Yeah, I like the terms. They're both small. They're both small.
There you
Really
go.
small.
Okay. Yeah, they're both really small, so definitely we want to keep them both. That was pretty simple. So maybe I'll ask you on the next one. What do you think about the r squared?
I don't like it.
You do?
Too low.
You don't
No,
like
I do
it?
not
Okay.
like it.
Yeah. So, so in a practical sense, what does that drive you to do or not do?
It makes me think there's a better variable that explains more of the change.
Excellent. Excellent. So it makes me a little bit loath to make predictions using this model, using the simple model of y equals b0 plus b1x, or y equals service level equals some constant or some slope times people hours plus a constant. That's it. So maybe there's another variable that I'll put in or what have you. Okay, great, wonderful. I've covered everything that I wanted to in the simple linear regression, and now I'd like to kind of extend in a couple of different ways so you can see them all. Maybe what we would want to do is, instead of just using these two, maybe I would want to add, as Dan said, maybe I want to add another variable into the mix. So what if I did that? Oh, I've got experience level here. Maybe experience level. So I knew that was coming, right? So what if experience level, what if we could add that into the mix? And like I said, we'll do this again on Friday, so we'll make sure that we cover this really well. But what if I wanted to add experience level into the mix? How could I do that? Well, it's just essentially using a different place in Excel stats. And so we were using 2 variables. Yeah, there's 3 variables. I wish it didn't have 3, or I wish it included 3 num. It doesn't. But it does have n num. So we're going to be able to use 3 or more variables. We're going to be able to do this. So let me go ahead and do that. I'm going to add experience level into here, and now we use n num instead. So far so simple. It's just a click of the button. All right, it says 5 variables to show on datasheet. Now that's pretty weird because I only have 3, but let me just go ahead and click on this. And it says, this is interesting, it says it wants my dependent variable. We'll get to that in just a second. Dependent variable is stat speak for what is my y, what's my output, okay? So I'll just show you that it's going to put people hours out there. We're going to want service level, but you can always change that later, and I'm going to show you how to do that. Okay, so what it does is it opens up a sheet, and you'll notice now we have other data that's in here. Now, I'm not sure why it gave us a blank, but it did, which I guess is fun. What I'm going to do here is, just like in other places, you can select the variables that you want. So I'm going to select people hours over here and service level over here. So what I've got is service level as a function of, there's a column right here. When I first opened this, I wondered what it was as well. This is for the constant term. If I want to get rid of that constant, I'll make that 0, but I'm just going to leave that here for now. And let's see what we can see here. So it's a little bit different because when I go to, if I go to, on the sheet that's labeled 1, I can make some plots of things, which is great. I can look at the histograms pretty quickly. But what I really wanted to do is look at those scatter plots, right? So if I look at scatter plots, I can look at one versus the other. So maybe I want to look at service level versus service level. That's not very interesting. How about service level versus experience? Yeah, well, it certainly looks like there's a high correlation between these two. And then here's my old one, service versus people hours. Not as strong of a correlation. Now, in the book and in Minitab, and a lot of statisticians put a lot of stock in a scatter plot matrix or a correlation matrix. It sort of does all of the scatter plots at once. Now, I like to look at them exactly this way, one at a time. There are advantages to doing it the other way, but I like looking at it one at a time because when I do that, I can see them. Watch what happens when I do a scatter plot matrix. And this is, mind you, this is only with 3 variables. What would happen if we had a bunch? So, okay, so maybe you can read this. If you can, you're a lot better than I am at this. But to me, this is really hard to read and is not telling me much. So I X out of this, and I hope to never see it again. So I guarantee, look, if you stare at it long enough, you'll see. A correlation matrix is interesting. And this will maybe tell you, for example, right here, there's a high correlation between service level and experience, and a sort of moderate correlation between service level and people hours. But it also tells me how correlated experience and people hours are together. So to a certain extent, this can help me understand the bigger picture, but not as much, I think, as looking at a number of these different things. Okay, so far so good. The real question is, did I actually get anything? Because look, it says this is my original regression. There's the 26% R squared, and there's the, oh, this is a lot better. Maybe I should just use one of these two. So the answer is no. We're going to incorporate both of them into the model, and we're going to do it by going over to multiple regression. So if you click on multiple regression, and I'm just going to blow this up a little bit so we can see it a little bit better. We see at the top, here's my equation. It says, aha, yeah, the service level is some amount plus some amount times experience plus some amount times people hours. So in other words, the format is, let me erase all this again. The format's a little bit different. Now you're going to see why that p-value is kind of important. It's b0 plus b1x1 plus b2 x2, where x1 is maybe experience and x2 is maybe people hours. Okay? Yeah, I think I've got that in the right order. All right, now you see that when we fit one, the other sometimes can be more significant or sometimes less significant. Now this is rather interesting. This is so close to 0.05, I don't know whether to reject it or keep it out or keep it in. I'll just tell you what I do when it's this close to 0.05. I tend to keep it in the model. I tend to be a little bit aggressive in keeping things in the model. But look at this here. This gives me an R squared that's better than either of the two alone. Remember, one of them said 26%, and the other, you probably don't remember this, but the other one just with one of them said 71%. So when we add in the second variable, we actually make our prediction much stronger. I mean, look at this. When adding in experience, we were able to make the regression go from 26% to 75%. That's a much, much better prediction. Now, I can't draw it in the same way that I did before, but I can still look at the residuals. I can still look at the fits in R squared. So let's just take a quick look at the residuals. There's my residuals. There's not a lot of pattern there to that one. So that's pretty good. Those are good residuals. So that's pretty safe. And then I can go ahead and make prediction. So for example, I could say, you know, I want to be able to staff. I want to see what the service level is going to be if I put an average experience level of 3 years experience, and I staff it with 10 people. What's my service level going to be? And this would predict my service level is going to be 78%. But actually, somewhere between on any given day, it could be between 71% and 85%. Over average, this is what we're going to expect. We're going to expect at 78, but somewhere between, our best guess is 78, but all bets are off between 75.6 and 80.6. Okay? So it gets a little more complicated because I have to use 2 things to predict. Now I have to keep track of 2 variables instead of just 1, but I did get a lot of prediction power. Hopefully that made sense to folks. Okay. let's I want to walk through one more example, and then we'll leave the other for next week, and hopefully I can let you get your hands dirty a little bit more. Actually, I'm going to pause for any questions that you had about this one before we move on. Pretty cool how we were able to move additional things in. And by the way, this works if you have many multiple things. You can really change a regression from not very good to something very strong. And a lot of modern regression models, like supposedly Netflix, has a tremendous regression model to help predict its inventory, where they're using something like 120 variables. I mean, it can get pretty serious. So, but I can tell you that in practice, there was an application where we at a financial services company in the Northeast, Hartford, Springfield area, where they were looking at times that it was going to take to, not times, maybe it was error rates. I can't remember exactly what it was, but it was some figure of merit where we were trying to predict for loan applications, and it just nailed it. I mean, it was like a 98% regression with only about 5 or 6 variables. So it explained everything. All right. So let's do one more. And for that one, I want to do lat long. So I'm going to do this one, and we'll probably come back to it. January temperatures. I want to do this just because I hope that this is going to be a harbinger of warmer temperatures in the Northeast. So here what I've got is I've got January temperatures. These are average January temperatures for a bunch of cities in the U.S. And we've got the latitude and longitude. And I'm going to take a bunch of things along for the ride. We're going to do nnum. And even though I can't do anything about city and state and temperature, I'm sorry, city and state, they're categorical. You find out that it's we'll find out that it's easy. The Excel stats nicely deals with it. All right, so I'm just going to leave these in, even though I'll show you at the end they don't do anything to the model. Excel statistics can't interpret letters here. It just ignores them. But here we've got latitude and longitude, and I'm taking this out for just a moment. So I've got latitude and I've got longitude in my model. Let's just start out with by looking at them. So here's the scatter plot. Whoops, I want January temperature versus latitude. So what would you say about this one? Pretty strong or pretty weak or what? How would you explain this particular scatter plot?
Strong negative correlation?
I agree. I think that's a very strong negative correlation. Is there anything else that you see in this scatter plot?
A lot of outliers?
Yeah, I see some outliers as well. And I'm going to circle the ones that I see, and you tell me if this is what you see. I see these two in particular, but maybe a few others. Maybe this one, maybe this one, and maybe this one as well. Maybe even some of these on the bottom. Make sense? Okay. Let's take a look at the next one, longitude. And somebody, I think that was Mike. Somebody other than Mike, tell me what you see here. Not a heck of a lot, right? This is kind of a blob. Yeah. But I do see something. I see these guys right there. I do see that. So that might be important, okay? I'm going to, at least for the moment, ignore that. And we'll take a look at the multiple regression model. So the interesting thing is, I might start out with just latitude to start this, right? So I might start out with this. And if I look at this, and I have my regression model, which is January temperature is 108 degrees minus 2.11 times latitude. I think this is degrees Fahrenheit. It has a pretty good R squared. And don't get too excited about the 108, because if you plug in the numbers for our latitude, folks, it's pretty darn cold up in the Northeast. So that's not too bad. And it certainly looks like the p-value is real. And if we did the residuals, I'm not going to do the residuals, but if we did the residuals, we're going to see the same thing in terms of outliers that we saw before. I guess I said I'm not going to do it, and here I am doing it. But there it is right there. See, we're seeing those same outliers. We're seeing maybe a bit of a pattern. It's above the line at the end and not in the beginning. So it's hard to say for sure. Let's add in longitude now. And what would be your guess in terms of the p-value of that being in the model? Whoops, I don't know what just happened there. I don't like it. Oh. If we add the longitude in, what's your guess in terms of the p-value that we'll see? Is it going to be greater than 0 or less than 0? Just a guess. I mean, look at this correlation. Not a very big correlation, right? I think most people would say it's not going to be a significant term in the model if we add in latitude. And I just wanted to point out that can sometimes be deceiving. And the reason is that, think of it this way, and we'll cover this more next on Friday for sure. Think of it this way: if you take a penny and you put it in your and you put it in a shoe, okay, and you give somebody 2 shoes, and you say which 2 of the same type of shoe, and you say which one has the penny, they're unlikely to figure it out. You can't really feel that penny. But if you take the penny out and just put it on your hand and say, or put it on if you weigh it itself, you certainly can measure the weight of the penny alone. So essentially what's happening here is you can't tell the effect of latitude alone, but when you add in, of longitude alone, but when you add in latitude, all of a sudden, when you regress out latitude, when you add it in the model, all of a sudden longitude actually is seen. There is a longitude effect, and it's significant. All right, so that's pretty interesting. You can actually strengthen your regression by something that does not look right away in the scatter plot like it's going to do anything. Okay, I find that pretty interesting, and it shows you that there really is value in building the model, and not just using the plots. Even though I'm big on plots, there's value in building the model. Look what happens if I take out latitude and just leave longitude. It still comes up with, oh, it's not significant. So if I were just going to use longitude or nothing else, I'd say, you know what, I'm not even going to bother using longitude because it's not important to keep in there. But once I put in latitude, now all of a sudden, when I regress out the average for latitude, when I take into account latitude, now longitude does look like it has an effect. Okay? And in fact, it improved it a tiny amount to like 73 to 74% regression. All right. Well, if we look at what are some of those outlying points, and I'm going to just we'll leave this for next time. We'll leave this for next time. But one of the things that we might want to do is we can look for outlying points here, and that might give us some clues on where to go next. But I'm going to stop with this and just kind of recap, and we'll call it a day because it is a day. So we covered a lot of stuff here today. We covered a lot of things today. We covered, let me just start out, we covered the whole innocent until proven guilty stuff. Remember that, innocent until proven guilty? Hopefully you remember that. We covered the fact that, look, this is in the analyze phase, or at the end in the control phase when we're doing these tests. All right. We covered p-value again. Remember, it's at 0.05. And then the most important thing that we covered today is all the stuff about prediction, right? We covered the basics of simple linear regression. Looking at a scatter plot first, that's always important. We covered correlation, always between -1 and 1. And the more important thing in building a regression model, because we can use that for predicting, but unlike just plugging in numbers like anybody can do in Excel, and believe me, anybody does that in Excel, we learned to do it a little bit differently. First by examining the fit. That wasn't important until we got to the multiple. That was really where it was a star. Okay, and we're going to do more of this on Friday, so you'll see it's really a star. And then we also learned on how to interpret this before we just go plugging in values, to look to see whether it's a strong model or it's a weak model, and then to look and see if it's a safe model by looking at the residuals. If it's strong and safe, then go ahead and predict to your heart's desire. We did that. At the very end, we just showed, first time we did a linear regression model, I'm sorry, a multiple regression model, where we showed how we can add things in to make a regression a lot stronger. Okay, that's it for today, folks. Good day. We'll see you on Friday. If you have any questions throughout the week, don't be shy to ask. And I'm going to stop the recording now, but I will stay on a little bit if you have any questions whatsoever. Have a real powerful week, and we'll see you on Friday.
Right. Thank you, Mark.
Mark,
Yes.
when will we be getting our next